So anyway, any questions before we begin? Like on what we did last time? Do you have any questions? Yeah. Mohammed? Yeah. Any questions on continuity? Yeah, we're not done, but so far, do you have any questions on what we did so far? We're going to finish it up today. There's only one part left. It's a part called the Intermediate Value Theorem. It's something that happens as a consequence of a function being continuous. So it says, suppose f of x is continuous on an interval a b, and that f of a is less than and less than f of b, then there is a number c in the open interval a b such that f of c is actually equal to that n. Right? This is called the Intermediate Value Theorem. It just means you always have some intermediate value inside this interval where you can hit every y value between these two. It's usually illustrated by a picture. Basically, this says at some point, this is your a and that's your b. Right? Let's say your function is doing whatever. Right? This would be your f of b. This would be your f of a. Now for any number in between these two values, n, right? Anywhere in here, right? Let's just say, for example, it's at this point. There will be a number c in between a and b such that that guy is equal to f of c. Right? So basically, if you're continuous, and you must attain all y values between any two given y values. That's basically what it means. Right? There will be nowhere that there's a gap or a jump that you're going to miss a y value in between these two non-equal y values. Right? That's basically what it means to have the intermediate value theorem. An application of this is being able to find roots. Well, not exactly finding them, approximating them. Because you only need really one. So here's the question. Could you actually find the roots to that equation? The fifth power polynomial? Can you tell me exactly what x will make that 0? So linear equations are easy. Quadratic equations are also easy. You have a quadratic formula. Cubic equations they're bad, but they're not so bad. You also have a formula for them. You have a formula for 4th degrees and 5th degrees, but those are crazy. Above a 5th degree, there's no formula that gives you a general solution for any general polynomial. So here you have a hard time actually finding a solution. But if you can sort of guess where one is, you can keep pinpointing sort of where it will end up. So here I actually show that there is a solution to this equation. Well, basically, show that this has a root call this f of x. A root is just a solution, an x value that equals 0. Right? So, i.e. x to the fifth plus 5x plus 3 equals 0 for some x in this interval. Right? So I don't know what the root is because I don't have a general formula for that, and I can't really factor that in an obvious way, so I'm going to try to use the intermediate value theorem to sort of pinpoint where this root is. What we can do then is actually try to find two y values that I know this 0 is in between, right? Note, if I take f of minus 1 and f of 1, well, I can like plug them in, right? If I plug in minus 1, I would get minus 3, which notice is less than 0, right? If I plug in positive 1, I would get 9, which is greater than 0, right? So this is like my f of a. This is my f of a here. This is my f of b here. Note, since zero is actually in between these two numbers, right? This is my n that I'm talking about in the theorem. This was the a, this is the b. By the intermediate value theorem, there must exist some number in this interval such that f of c will actually give me that number 0, right? So I don't exactly know what that number is, but I know it has to exist. There's definitely a 0 to this function in this interval somewhere, right? So you can't really tell where it is, but you can approximate to any degree of accuracy, right? What you can start to do is start to break down the intervals even smaller, right? What about between minus half and a half, minus a quarter and a quarter, right? You try to make the interval smaller and smaller, and you can always prove that something is in there. So you can approximate to any degree of accuracy if you're patient enough. But this is just to prove that you have to know that it's out there somewhere, right? You can actually use what's called the intermediate value theorem. Because this function is continuous, it's a polynomial. Right? F of x is and so is continuous infinity. In particular, continuous on minus 1 over 1. And that's basically it. Told you his longboard wasn't working, he doesn't even have it. Broke with a coffee machine. That's basically it, right? So you take a continuous function, and if you can prove that it will attain every value between any two non-equal y values, if it's provided it's continuous on every floor. So this way you can approximate zeros to functions that you don't really have a way of finding zeros otherwise. And that's pretty much it for 1.5. So the homework for that is due tomorrow. Some people are smart and already started it, so you guys can do tutoring center. We're moving on to 1.6. Limits involving infinity. So we talked about these two guys before, 1 over x and 1 over x squared. Now I told you that this guy did not exist because of how the graph looks, right? And this guy we actually defined to be plus infinity because the graph looks like that, right? As you're going from the left to the right, you keep going up and up and up, right? But we didn't really do this formally. We're not going to do this super formally anyway. But we're going to sort of talk about what does this mean? What does it mean to say the limit is plus infinity? Right? What does it mean to say the limit is minus infinity? Okay. So, here's these limits. Limits at infinity. Limits to infinity. There's a difference between this one. So, we say limit of x approaches a of f of x equals positive infinity if for any n greater than 0 we can make f of x greater than n by letting x get sufficiently close to a, right? So this means at some point, so if I want to illustrate with this graph again, just to illustrate this picture. I'm saying when I say it's equal to plus infinity, I mean no matter what positive number you pick. Let's say you pick your n to be a positive number that you can plot on the y-axis here. All I have to do to make sure f is bigger than that number, I just need to make sure my x travels this close, right? In this case, my a would be here. I just have to make sure x travels within this distance of a, and then I would have passed that value. Or you say, okay, what if I pick a higher value? Well, I just make it go even closer to a, and it will pass that value. What if I pick a bigger value? I can make it go closer to a to pass that value, right? No matter what positive number you give me, my function will pass it eventually, right? That's what it means, right?
Professor,
yes.
So for this, why would you say does not exist?
Right, because the limit don't connect. It's a one-sided limit.
And
so sure, if I'm approaching 0 from the right, then yeah, it will pass any positive value. But that's not true if I'm looking at the left. Right? Yeah. It approaches negative infinity in exactly.
So you are only looking for the y values, right?
Yeah. Limits, remember, you're only looking at the y values and both sides have to match up for it to exist, and we call it something. Right? And limit. Similarly, as x approaches a of f of x equals negative infinity if for any n less than 0, we can make f of x less than n by making x sufficiently close to a. Right? So in the case of something like minus 1 over x squared, the graph would look like this. No matter which negative value you pick, eventually if I get close enough to 0, I'll be lower than that. Right? I can get lower than any number you pick. Right? By just approaching a close enough. In this case, a would be 0. That's sort of what it means. You can keep getting higher, 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 or lower, lower. Okay. Now for some terminology.
Professor,
Yes.
over there it says f of x equals negative infinity. How do you know that there are 2 points going to negative infinity?
How do we know that one?
How do you know that 2 points are going to negative infinity? 2 points approaching from left and right?
Yeah, you check it. You check it. Right? It depends on the function, but you'd actually check both.
So you name the origin as an A?
In this particular example, yes. It's not always the origin. Right? It depends on what function I tell you. In this case, I'm looking at this example.
Okay. So
Right.
wasn't that
Different
supposed to
functions.
be, so wasn't that supposed to be on top, like f of x equals negative 1 over x squared?
Yes. That's a particular example here. This is in general. This is a general definition I gave you here.
Oh, okay.
I just illustrated it with this particular function.
Right. I was just confused because I thought that up one was the graph from the bottom.
Oh, no. This is a general definition.
Okay.
Saying this for any f of x means that this happens.
Okay.
This is an illustration. This is a definition or notation. We say f of x has a vertical asymptote at A if any of the following are true. Then as x approaches A, f of x equals plus or minus infinity, or the limit as x approaches A from the left is plus or minus infinity, or the limit as x approaches A from the right is plus or minus infinity. Anytime you approach something and you get an infinite limit, you say you have a vertical asymptote at A. So for example, this function, 1 over x squared, has a vertical asymptote at 0. Right? Means there's a point, at 0, your function cannot attain any y value. Right? In that case, you say it's a vertical asymptote. We're going to come back to that later. When we're graphing things, we're going to ask you to find vertical asymptote and horizontal asymptote. For example, how would I find the vertical asymptotes there?
Just plug in 0.
Set the denominator equal to 0, right? Set x minus 1, so this gives you x equals
Plus 1.
plus or minus 1, right? These guys will give you vertical asymptote because as you approach and either of these values, your denominator goes to 0 and the function goes up. So x equals 1 and x equals minus 1 are vertical asymptotes. So these are the A values, right? As you approach either 1 or negative 1, your graph goes up. We'll actually come back to that. We're going to come back to graphing functions and we'll actually see what the graph of that would look like. The limits at infinity, these are, we can actually let the x get large. Right? Let x itself go to infinity. or negative infinity. Right? And sometimes you can get a value, sometimes you won't. So maybe I should say what that means. Anyone want to give me an example for this that illustrates that definition?
Is that L? Is that L?
Yes, big L. It's whatever the limit is. Turns out we can use the same example as an illustration. What if I say x goes to infinity of 1 over x squared? What do you think that answer would be? Right? Is there a number that I can make my function get very close to that as x just keeps getting huge? 0. If you look at the graph again, right? This thing is getting smaller and smaller and smaller, approaching 0. So no matter how close you want me to make it close to 0, I can get it there, just make x bigger and bigger and bigger, right?
You never touch 0.
I'll never touch 0, but I can get as close to it as I want. All I have to just do is travel to the right a little bit more, right?
So you put the not like this. Oh, it's only going on one side. No.
No, it's actually 0. I'm looking to infinity, so I'm only looking to the right. I don't care what's happening with there, right? I'm letting my x approach infinity, right? Letting it get huge. And what's happening is the graph is getting closer and closer to 0, right? And I can get as close to 0 as I want. All I have to do is make x big enough.
So it doesn't matter how the graph looks because the 1 over x squared is supposed to be like this, right?
Yeah.
So you don't care about the left side?
No, don't care about it at all. Just as x is getting big, what's happening to the function, right? Also, so this is actually equal to 0. Similarly, if I take the limit as x approaches negative infinity of 1 over x squared, what would that answer be? It's also going to be 0. Because if I'm letting x go to negative infinity, this will keep getting close to 0 as I like. Right? It won't do that for any other number. Right?
So
That's
because
why I
I
say
was confused on that. You said you never touch 0, then how can you get 0 as an answer? Is it just getting close?
closer to 0. Remember, limits don't care about getting there. They care about getting as close as you want.
But getting close was the limit as x approaching to infinity. That's the closer one, right? The answer is not supposed to be close. It has to be exact, isn't it?
Not for limits, no.
Okay.
We've done examples like that, where we found a limit to a point where the function was undefined. So you can't actually touch that point.
The answer that we're getting is for the y, right? Not for the x.
Yes.
Yeah. So isn't that has to be like an exact?
Example, but I mean, we've done examples like this before. Limit as x approaches 1 of x squared minus 1 is over x minus 1. Right? What was that? That was actually the number 2, right?
Yeah.
Right?
So it goes in x plus 1 and x minus 1.
Yeah, so you cancel, right? X plus 1, x minus 1, so x minus 1, and then you plug in 1. Now let me ask you the question. Do we ever actually attain the y value 2? Do you think we attain the y value 2? We can check, right? Suppose our function equals 2. What would that have to mean? This would mean that x squared minus 1 has to be equal to 2x minus 2, right? That would have to mean that x squared minus 2x.
Wait, how we can check? Oh, you multiply by the x.
Well, that's not going to be right. So you have x squared minus 2x plus 1 equals 0, right? Now if you solve that, you'll get x equals 1, right?
Yeah.
Now what's the problem with x equals 1? You actually can't touch it. The only way for your y value to be 2 is if your x value equals 1, but you can't make the x value 1 because you're undefined there. You divide by 0 to make x equals 1. So the only way you can touch 2 is if you make your x a value that it actually can't be. Right?
Yeah.
And so that means you actually will never hit the y value 2. Right? This graph looks like there's a hole here, right? When this is at 1 and that is at 2. You'll actually never touch that point. You can't touch it. You touch it, you divide by 0, and math blows up. The universe gets destroyed, and then destroy the whole number system, and then kill the internet, and all sorts of things. Bad things will happen.
Shouldn't be first.
You think I'm kidding? You divide by 0, you pretty much kill math. Like, it doesn't exist anymore.
Wait.
Like, you can prove that if you can divide by 0, you can actually make every number equal to every other number. So your whole number system is dead, because there's only actually one number. And then you can't add anything, you can't multiply, you can't do anything, because all you have in the universe is a number. It's just this one guy that's equal to everything. It's really weird. Okay. Yeah, I'll actually prove that on the test. I should probably do that. Okay. Right, so remember, limits always deal, whether you're talking about the x or the y, it doesn't matter. I'm talking about getting close to something. You don't have to actually be able to attain it.
So x and y both are getting close.
Yeah. It just means you can make the y value close to this if you make the x value close to something else.
Yeah, I was confused on whether the x was just supposed to get close and the y has to be exact. So
No,
both has to
both,
be.
it's all about getting close. All right, for both of them. Okay. By the way, these two guys illustrate a very important point. It's actually, I don't know if I can call this a theory. It's not big enough to be called a theory. But you should notice that this has a rule that we're going to use all the time. The limit as x approaches plus or minus infinity of 1 over x to the n is actually equal to 0 for any positive integer n. And the reason you can sort of see is that 1 over x to the n for positive n looks like this if n is odd. And it looks like this if n is even. In both cases, as you're approaching infinity, you're getting closer to 0. When you go to negative, you're getting closer to 0. Same thing here. Whether you're going to positive or negative infinity, your y value is leveling off at 0. It never hits 0, but it gets closer and closer and closer to 0. And we can actually use that to our advantage to do a bunch of different kinds of limits. For example,
We actually copied the no.
I did this before.
Yeah, but without the limits.
All right, we're actually going to use it now. Let's say I ask you to compute the following.
You know the power function? I don't know if you can recall. We can
Right.
repeat that power function.
I also talked about infinity before, which technically I shouldn't have before this section. So I don't know. How do you find that one? Let's great difficulty.
Is it a half?
You consider leading terms?
Huh?
You take the leading terms, right?
Right, but why does that work?
Because when you plug in infinity, that's the one that's going to increase the most. That's why.
Yeah, that's actually true. Like, but I want to show you the long way to work it out first, because that might help you with other kinds of problems. But yeah, at the end of the day, we're going to actually do a summary here, which basically is going to say what we're going to say. But I think it's beneficial to do it the long way also. Alright, so what's this one equal to?
It's equal to
Yeah.
a half.
It's actually equal to a half. Now, how would you prove that? The trick. Divide the numerator and the denominator by the highest power of x in the denominator. Right? X is not 0 because we're going to negative infinity, so we can divide by it. Right? So this guy will be equal to the highest power of x in the denominator is x cubed. So what I'm going to do is divide everyone by x cubed. X cubed over x cubed plus 5 over x cubed over 2x cubed over x cubed plus 1 over x cubed. This you can actually simplify. This does cancel, right? You just get 1 plus here you have 5 times 1 over x cubed. This will cancel. Here you get 2 plus here you have 1 over x cubed. Right? Now, based on this rule that I just wrote down, what can you say about the limits? Well, this guy is going to go to 0, and this guy is going to go to 0. And so the limit here is actually a half. Right? You can sort of do the same thing with this one. What would happen with this one? Divide everyone by the highest power in the denominator. What would you get? 3x squared over x to the 4th minus 7 over x to the 4th all over 2x to the 4th over x to the 4th minus 3x over x to the 4th plus 1 over x to the 4th. And so this would give us 3 minus 7 over x to the 4th. No, well, 3 over x squared. And this is 2 minus 3 over x cubed plus 1 over x to the 4th. And what happens? Well, this would go to 0 by that rule. This would also go to 0. This would go to 0. This would go to 0. I end up with 0 over 2, which is 0. What do you think would happen here? What's the answer here? You think it's negative infinity? What's negative infinity? Does everyone agree with him? It's negative infinity?
I'm going to agree too.
Huh?
I think I agree too.
Do you think this is negative infinity?
Okay, I don't know.
Jeez, stop firm on your Let's do the same thing.
I think it's negative infinity divided by positive
divide everyone by x squared, right, which is the highest power of x in the denominator. X cubed over x squared plus 3x over x squared plus 4 over x squared over 4x squared over x squared minus 2x over x squared plus 1 over x squared. This gives us 2x plus 3 over x plus 4 over x squared over 4 minus 2 over x plus 1 over x squared. By our rules, these all go to 0, these all go to 0. So what I have is actually x over 2, right? This thing will simplify to x over 2. Now as I'm making x go to negative infinity, what's going to happen? I get negative infinity. X goes to negative infinity, this means that this x will go to negative infinity. So it's actually negative infinity. So Rashard would have been like, that looks wrong. Change your answer. Okay. It's actually negative infinity. Okay, can anyone tell me the general rules here? Did you notice something? Yeah? Can you state a rule? Your first theorem?
Wait, I was going to try to say that as a limit, like as the x approaches negative or positive infinity, like it has to do with the highest exponent in the numerator.
It has to do with the highest powers. Okay, how would you state the theorem in terms of highest powers?
So, if the highest power is the denominator, it's the
I suppose p of x and q of x are polynomials. Then the limit as x approaches plus or minus infinity of p of x over q of x would be equal to, there are actually only sort of 3 possibilities, 4 to count, the last one. What would it be? So you get 0 in one case, and you get 0 in the case of what? The degree of q is greater than the degree of p. Right? You understand what degree means? It just means highest power. So as long as the power of the bottom is bigger than the power of the top, this will always go to 0. Because when you divide everyone by the highest power here, this guy is going to give you 0. Another option is you can get plus or minus infinity, as in the last example. This happens if the degree of p is bigger than the degree of q. Right? The plus or minus, you just have to watch the signs. All right? So in this case here, x is a negative number, which is why this went to negative infinity. If I had made this plus infinity, it would be plus infinity, right? You just watch the signs, how they work each other out. But it's going to be infinite. And the more technical one is the last case, which is what? If the degree of p is equal to the degree of q, what is the answer? Yeah?
You divide the coefficients of the lead variable.
Right. Leading coefficient of p divided by the leading coefficient of q. Right? In other words, the ratio of the leading coefficients gives you the answer to the limit. Right? So knowing this, which I will allow you to use this without justification, you can do any limit that looks like that pretty easy, right? So Okay, so those 4 examples. What is this equal to? Huh? Negative infinity. What is this equal to? Negative a half. What is this equal to? Negative 2/3. What is this equal to? 0. That's correct, right? Just like that. Right? All you're doing is looking at the highest powers. That's all you're doing, right? Because the highest powers, as you get bigger, these guys get so big that all the little guys just don't matter at all. You can pretty much ignore them. That's sort of what you learn from the limit rules. Yes? You find the leading coefficients. Right, this is +2 minus 3. Huh? This one? Right, well, you just look at the leading ones, right? Right? If you look at the leading ones, what will happen? Right, it would behave like x cubed, because you're only looking at the top guys. Now, as you plug in a negative answer into cube, you get a negative infinity. Right. So in this case, one thing you have to look out for is the signs. It actually depends on the function whether you go positive or negative. You just have to watch the signs to see, okay, if I'm going to positive infinity, I know this coefficient is positive, that's negative, this is what's going to happen. Right. But essentially what this rule gives us is that we can ignore all the little guys. Right? And later in talk 2, when you learn about exponential functions and log functions, and they start throwing those in there, you know which functions to ignore for the limit, which functions to consider for the limit. Yes?
If 4x ends up being squared, it would be positive instead of negative?
If, in this example?
Yeah, if it ended up being squared instead of cubed, it would...
Like here, if I had put an 8,
Yeah.
it would have been positive, yes. Yeah, so you really have to, for this one, you have to watch the functions and the signs, because it will affect the behavior. Right, to determine it's plus or minus, you just look at it. But in the grand scheme of things, that's minimal. You know. It's a lot easier than having to do this. Okay, so that's a general rule that we can apply. You can know this limit by any one of these cases. All you do is watch the biggest guys.
So Professor, whenever the q degree is bigger, you can just write straight 0?
Yes, whenever the power on the bottom is bigger, it's 0. It'll always be just 0. Just ignore everything else.
Negative, positive doesn't matter, right?
Doesn't matter, because negative 0 and positive 0 are the same. Right, so here, the biggest power here was 8, the biggest power there is 6, the biggest is on the bottom, it's 0. Just don't even worry about it. Anything else they tell you is just confusing. Right, they might say, oh, you know, pi x to the 6. Oh, everyone, oh no, I don't know pi, what is the sign of pi? No, it's a trick. You're looking at the biggest powers. Right? I see that happen all the time. Like people, oh yeah, this is easy, pi. E, ln. No, don't let your brain shut off. They will make it look scary. You're only looking at the highest powers. That's the only thing that matters if you're going to infinity. Right? Just make sure you know that. Okay, what else do we have to talk about here? Okay, so if, another definition, if, as we take the limit as x goes to infinity of f of x equals L, let's call this L1, or the limit as x approaches negative infinity of f of x equals L2, then y equals L1, and for y equals L2 is called a horizontal asymptote. So this is saying as you're going to infinity or near infinity, your y value is actually leveling off at a number. And we shall assume that these are finite numbers. They're not infinite. I should mention that. So L1 and L2 are finite. For example, let's go back to the formula we had before that we tested the vertical asymptotes for. How do you find the horizontal asymptotes?
This is 0.
It's going to be 0. You check both limits, right? Take the limit as x goes to negative infinity of x squared, x over x squared minus 1, and you find the limit as you go to positive infinity of x over x squared minus 1. By the rule we just did, the highest power is on the bottom. This is 0. And this is also 0 by the same logic. So y equals 0 is a horizontal asymptote.
Did you go to the vertical one?
Huh?
Did you go to the vertical one?
Yeah, we did that earlier. Not paying attention. Or we're going too fast.
Yeah, you're going too fast.
No, the funny thing is we're actually going too slow. Yeah, totally.
So if you have 2 different values for them?
On average, I cover like 1 section a day. If you count the number of sections and the number of days of class we actually have, you'd realize I'd have to be covering 2 or 3 in a class. Yeah.
So if you have 2 different values for the limit of
Two separate, you have 2 different.
horizontal asymptote,
That is possible. And later on we'll do examples of that. I believe in chapter 2 or 3. You'll see things like that happen. Challenge. Can you do a, I don't expect you to do it in detail, naive sketch of this function?
Is it nice or not?
If you had to draw a picture for that, what would you guess that it looks like based on what we've done with it so far? Just mentioning that. But some things to look out for. Anyone have a sketch of this yet? Do you have an idea what it looks like?
Sort of like, yes.
Almost. Almost. indeterminate form. This is a topic you'll cover in Calc 2, but I think it's worth mentioning here. If your limit attains the following values, the answer is not obvious. And I'll explain what that means. Things like 0 times infinity, or infinity raised to the 0, or infinity minus infinity, or 0 to the 0, or 1 to the infinity, or 0 over 0, or infinity over infinity. I think that's all of them. Right, so you might think these answers are obvious, but they're actually not. And they can pretty much attain any value you feel like. So don't assume that you know. Right? 1 to the infinity is not 1. Okay? 1 to any finite number is 1, but not infinity. It doesn't work here. Right? So don't think that if you see this happening, it's automatically infinity. It's automatically 1. 0 to the 0 is also not 1. Right? Any non-zero number to the 0 is 1, but not when it's 0. Right? So watch out for that. Infinity minus infinity is not 0. As it turns out, there are different sizes to infinity. One infinity can be bigger than another. It sounds crazy, but it's true. Trust me on it. Okay. I mean, to prove that's true, I'd probably have to teach you set theory. But we go. Infinity to the 0. You want an easy example? Yeah.
How many?
We will be doing examples of this. You're right. Yeah.
How many numbers are there? How many odd numbers are there?
What? How many what numbers?
How many odd numbers are there?
Yeah, infinity. Right.
Those are infinity, but one is definitely larger than the other.
What was your first set?
Just how many numbers are there? How many?
Oh, you mean real numbers?
Yes.
Yes, that is an example. There are actually more real numbers than there are even integers, even though you have infinity of both. Right. So these things, whenever you throw in like infinity or 0 to the 0 or division by 0, like arithmetic doesn't work. Do not assume you know the answer. It just won't work as you expect. It turns out infinity times infinity is still infinity, but negation actually won't work. And there are simple examples we can do with some of these, like the 0 times infinity one. What if I'm looking at limit as x approaches 0?
Professor, what do you do when you get in this situation?
Oh, you have to look at the function. Like for example, here. What's that level? It's actually a 1. How do you know? Well, you can simplify it, cancel. But if you look at the pieces, what does it actually do? The x would go to 0. 1 over x goes to what by our previous theorem? It actually goes to infinity. So this, in pieces, it looks like 0 times infinity, which you say, what, is it 0 or is it infinity? Because 0 times anything should be 0, but infinity times anything should be infinity. What happens when you put 0 infinity, right? What happens when an unstoppable object meets an immovable object, right? You can't have an answer. Turns out it could be anything, right? In this case, it's 1. It could have been 2, or pi, or 17.3. It can be anything. 0 times infinity can literally be anything. You just have to look at what's going on, right? You just have to pay attention, right? Same thing with these guys. They can literally be anything. And we're going to do a couple examples soon. Anyway, now you sketch it.
Is this it? Again, I can draw personal life.
No. Like most of you have like one of the parts right, but the other two are messed up. I think someone had 2 parts right. So
No?
That's it. So here's the idea. How would you figure it out? Well, the vertical asymptotes are at -1 and +1, right? You can't actually touch these values because you divide by 0. Then we said, as you're going to infinity, right, your y value should be going to 0, right? So the horizontal asymptote is actually the x-axis. So you know that when you're going way out here, your graph should be settling to 0 somehow, right? It should be settling to 0. And if you're in here and you're going towards that way, you have to be going to infinity, either negative or positive, right? Now, in this graph, you will notice that if you approach -1 from the left side, from the right side, what actually happens here?
What are we paying about?
Let's say, pretend you're like -0.9. What would this be? Positive or negative? This is -0.9.
It would be
Down here would
negative.
be,
It would be negative.
it would actually be positive, right? Because your denominator would be negative, and the top would be negative. Negative divided by negative, positive. So you know your graph.
It wouldn't be square. Square is not negative.
I must have got to mix up with another problem.
No, if this is 0.9, 0.9 squared is less than 1.
Okay.
So you -1, you get negative. This would also be negative, so overall it's positive. So it means that if you're approaching here, you're approaching infinity, but positive infinity. So your graph is going up, right? It's going up as you move in that direction. It actually has x-intercept 0, because clearly x is 0, it's 0. And if you look over here, you'll realize that it's approaching negative infinity, right? Pick x equals something a little bigger than, like positive 0.9. We'll get negative. So a naive sketch would be something that looks like this. Right? You want it to do like that, so you're kind of making an asymptote, right? It can't be a straight line because you just crash into the wall, right? It has to like curve like this to sort of level up. Similarly, it has to curve like this to sort of level up. So the middle looks like that. Now you know on the ends you're approaching infinity.
So isn't it horizontal asymptote 0?
What?
Isn't it horizontal asymptote x y equals to 0?
Yes, that's what the ends are going to be, right? Now I just figured out in the middle. Now what about the left and the right end, right? Let's look at the left side.
So if you say asymptote, you can't touch them that way.
You can touch horizontal asymptotes, you cannot touch vertical ones. There's a whole chapter on curve sketching. We'll make this precise later on. I just want to see if you guys are sort of seeing the idea before.
We'll go positive infinity.
It's definitely approaching 0 as we go out to negative infinity, right? We did it here. But is it above here or below here? Well, again, you watch the signs, right? As your x gets negative but huge, what happens? This would be positive and huge because it's a square. The top would be negative. So as you go out here, you expect your graph to be underneath. It'll be negative, approaching 0, but from the negative side. Because your x values would be negative. So it sort of means that this would happen that way. Right? You know it would have to go down because if you actually plug in y equals, if you set this equal to 0, there's only one solution here. Which means you'll never cross the x-axis unless you're at the origin. So I know it can't go up, it has to go down, right? Similarly over here, as x gets large and positive, the graph is positive. So it has to look like that. I know it's approaching 0 as I'm going here, but I'm positive. If I'm going that way, I can't go down because I have to cross the x-axis. The only place I cross the x-axis is the origin, because if I set that equal to 0, that's the only solution. So I know I can't go down, I have to go up, right? So you go like that, right? So this would be a nice sketch, and we're going to do things like that all the time. But you can sort of guess, like, that's what it would look like.
So if we can touch the horizontal asymptote, why don't those two other?
Like, for example, here we touched it. Here we touch y equals 0.
So why can't we touch the other one? Like the one on the left?
Because you can solve for it, right? If you set y equals 0, that would mean x over x squared minus 1 equals 0. A fraction is only 0, but the top is 0. It means the only place y is 0 is when x is also 0. So the only place you cross the x-axis is here. can't touch it anywhere else. This tells me that.
So, if you have one that actually is a line where the curve gets close but cannot touch,
That's not exactly true. That's true in the case of vertical asymptotes. We will see cases where the graph actually touches a horizontal asymptote. This is one of them. Horizontal you can touch, that's no problem. Verticals you can't, because verticals happen when you divide by 0. You just can't do it. Let's do some examples of things like these. Where, no.
Yeah.
What are you talking about? Web time. You have like 5 whole minutes. You know how many examples you can squeeze in 5 minutes?
Don't tempt me.
The first lesson will come back from the break.
And our quiz is going to be tomorrow.
There's a quiz tomorrow. Yes.
This is continuing because the next week we don't have too many classes.
The first test is up to this section, up to 1.6. So I like to give you like a week after I finish the section for the test, but next week, Thursday, we don't have class, so I can't do that. So we have to push this out. Well, Tuesday is less than a week from today, so I don't want to give a test that week. On Tuesday, we'll have a regular lecture.
So tomorrow, take it the Thursday after?
And
Tuesday. A week from now?
What?
Take it like not next week, just after that day?
No, like the Tuesday. We have the Tuesday.
Oh, okay.
Okay. So the week we come back, that Tuesday. Well then, wait, the week we come back. So September 30th then. So we can come back next Tuesday, the 30th.
Yeah, we'll finish off the section.
So are we done with 1.6?
Yeah, this would be the last final example.
Which means 1.5 and 1.6 is due tomorrow. And what is
Well, if you know the tricks and you know what to look for, it shouldn't take you that long.
on paper?
Here's an example. It looks like infinity minus infinity. Is the answer actually 0? How do you know? I could be tricking you and it's actually 0. How do you find that limit? The limit of this. Right? You can't just say, oh, x goes to infinity, this is infinity. X goes to infinity, that's infinity. Infinity minus infinity, the answer is 0. Huh? You can do the conjugate, right? You can actually multiply by x squared plus x over radical of x squared plus x plus x.
You can do that with that without the denominator.
No, you can't do it without the denominator.
Oh yeah, it is like
Because
over
you'll
1.
change the value of the limit, right? You have to multiply by 1. Now, what would happen in the top? Difference of 2 squares takes over, right? I get x squared plus x minus x squared. On the bottom, I would just have this.
Radical x squared plus x.
Wonderful.
So these guys die. Now,
And the x dies as well. The x dies as well.
how the x die?
The one on the right. It's a plus. No.
Positive can't cancel across them.
It's the no tolerance rule.
It's the blasphemy.
Automatic 0.
Yeah, it's 0.
That's an automatic 0.
It's the blasphemy.
You scared?
How would I do this?
Now.
It is just 1.
You try to factor out an x, right? Here, you can take an x squared out from under the radical, you factor x squared out of this expression, you get that.
Oh.
Right? Because if you multiply out, you'll see you get that. Right? Plus x. Now, is the radical of x squared just equal to x? No.
Yeah.
Yes.
Yes.
No. This is actually equal to absolute value of x,
Oh, yeah.
which is not always x, right? But so it can be plus or minus x. What is it in this case? Huh? Why do you say plus? Because what? Because you're going to positive infinity. Our x's are all positive values. You're on the right side of the x-axis, so x is positive. So this can replace with positive x in this case. If I was going to negative infinity, I would replace it with negative x. Right? So in that case, now I can actually factor out an x and cancel it. This cancels now, and what's the actual answer? It's actually a half, right? So in this case, infinity minus infinity was a half.
Wait, how do you
Oh,
get it?
it's 616.
What?
If it's a negative, you have to make a
Because as x goes to infinity, this goes to 0. So I just have radical 1 plus 1.
Divided by infinity is 0.
How do you know that?
What?
Keep on going, just like.
No, 1 over x goes to 0 as x goes to infinity.
This one. Yeah, this one.
So don't you do the LCD there?
Not expression.
Don't you do the LCD?
Just 1 over x makes it 1. So that's all that is.
I know,
Alright? This goes to 0.
I got 7 hours to do it, so I'm waiting for it.
Raise 1 over x to the n.
Oh, it was because of the rule, right?
The rule, yeah. I mean, we just go to the way home. So that just goes to 1 over 1.
It works out.